Hi everyone, and welcome back. So we will be discussing for a warm-up Coulomb's law. So when you're talking about Coulomb's law, it's kind of like the basics of electromagnetics, right? You have a charged particle, it emits an electric field, and it affects the electric field at a point in space. Okay? The basic formula for your Coulomb's law is that for a point charge, the electric field emitted by the point charge is equal to this equation that you see right here. Okay, so this r hat is a unit vector that points to the direction radially away from the point of your point charge. Okay, so this is the basics of Coulomb's law. Now, what if you have a charge distribution? Each point on a charge distribution can be thought of as another point charge, a very small point charge right here. There's also some small point charge on the other side, such that they affect the point in space separately. Okay, so this charge Q2 has a small electric field that is from itself, it's contributing an electric field at a point in space. Same goes with dq1, that electric field. Okay, and now because of this distribution, it also happens in a surface charge. Okay, if you have all of these small points that can be thought of as individual point charges, they affect the electric field differently, like this. Okay, to calculate the electric field of this setup, if you have a random setup, the electric field, if you want to calculate it by hand, you just get the integral of all of that. Okay, you integrate this charge distribution, okay, over all the different points in space. All right, R here represents the point in space, the coordinates, or the vector from the origin, okay, pointing to the point in space. R naught represents the position of your corresponding dq. Right? So you integrate this. Well, in this series, we're talking about numerical analysis, right? Once you have tried to solve this equation here, then how will you verify your answer if it's kind of correct, right? So for me, like I tried to solve for the line charge density, right? A basic example from textbooks. You can also solve the surface charge density. I've tried solving that. Well, sometimes I kind of doubt my answers. So one way to verify if my answer is correct is if I integrate it in my computer, right? But a computer cannot handle continuous data. It can only handle digital data. So what we can do to solve this numerically, maybe using Octave, is that we break up the charge distribution into different points and model them as point charges. And then add the effects of all of these individual point charges towards a certain point in space, and we can get the electric field. Okay, and we compare that to what we got analytically. Okay, so you just need to convert this integral equation into a summation equation, because the summation is what your computer can handle. Okay, so this is just changing your integral into a summation. sorry, uh, right here. Okay, so the electric field at a certain point in space, defined by R, okay, will be the sum of all the effects of the individual charges, okay, and their corresponding positions. So you add them all up, you get the electric field. So for your electric charge, line charge density, if it's on the z-axis, okay, the expression is okay, so this is the electric field for the line charge density. So what does this mean? Well, it just means that your line charge density emits electric field, okay, perpendicular to it. The electric field expression for your surface charge density. So, sorry, I forgot to mention that rho L here is the line charge density, which is in coulombs per meter. For your surface charge density, the electric field is actually a constant. Okay, A n hat here corresponds to the direction that's perpendicular to your surface charge. Okay, so this is the electric field expressions as we know it. So let's verify them using Octave. Okay, so for your Octave simulation, you have a surface charge density at z is equal to 0. Sorry, you have a surface charge density at x is equal to 0, y is equal to 0. So that's the z-axis. And your surface charge density is at z is equal to 0. That's your xy plane. So let's see how they will turn out when we try to simulate them. Okay, so now I will discuss the code for solving numerically the line charge density of the electric field of a line charge density. Okay, so let's go through this step by step. The first few codes are just to clear the uh, current workspace and to close everything that's open, other windows. This is your line charge density. Let's assume it's 1 nanocoulomb per meter. These are just the spacing between the lines. Okay, so your grid will be based on this, just the spacing. Now, this part of the code creates the space, the three-dimensional space for MATLAB. At first, we defined the raw direction. Okay, this is the for the cylindrical coordinates. So for other textbooks, it's R. Okay, but for electromagnetics that I know, we use rho. Okay, so this defines the limits of rho. Okay, for the radially outward from the cylinder. This defines theta. In other textbooks, it's phi. It's from 0 to 2 pi. We're looking all around the cylinder. And the z-axis is, well, you already know what that is. The mesh grid commands creates the three-dimensional space for your cylindrical coordinate system. And we convert the cylindrical coordinate system to Cartesian because that's easier to draw here in your Octave, not MATLAB. Okay, it's Octave. All right, so now you have your three-dimensional space. This command just clears R and PH to free up some memory. This is your constant. Okay, this here, oh sorry, this is not dE, this is dQ. Since it's constant, okay, since it's constant, dQ is equal everywhere on the line charge. So this is a constant line charge density, right? And now we just solve for the x, y, and z components. The first thing we need to do is to initialize basically our vectors. So the vector has three components on the x, y, and z plane, as you all know. And for this loop, we just solve for the contribution of each line charge to a certain point in space. So this EX, EY, and EZ matrix here is actually, it's not just the electric field that's found at each point in space. It also stores the the contribution of the electric field from the different points of your line charge density. Okay, that's why the dimension of this is 4. It has 4 dimensions actually. So that's what's happening here. This is just the denominator for your uh, electric field expression, and this one serves to calculate the contribution of each point of the line charge density. Okay, and stores them into your EX, EY, and EZ matrices. Next, this command here adds the contribution. It's basically a numerical integration. It uses the trapezoidal method of numerical integration. Okay, so this is a command. We'll use a different command for the surface charge density, but don't worry about it now. Just think about it as numerical integration. Okay, so the trapz command is that. So yeah, now you integrate EX, EY, and EZ after storing the values at each point, okay, on the matrix. You end up with a three-dimensional matrix after this, and you just plot it. Okay, so let's see. Okay, oh sorry, raw. Yeah, sorry. Why is not raw is not here? I deleted it earlier. It's equal to 1 earlier. So anyway, okay, there we go. So this is now your line charge density and the corresponding electric field. So earlier we said that the electric field points radially away from the line charge density. Since the computer has a finite memory, this line charge density is not actually infinite. It's a finite line charge density. But we can see that the results are close to what we solved from analytical solutions. So we can be confident with our solution, my analytical solution from here. Okay, now let's move on to surface charge density. So in the same way, let's define a constant surface charge density. Okay, and these are just constants. Why is this dE again? This should be dQ. I apologize. Okay, right. So this is just a constant corresponding to the effect of the surface charge density. And we just already factor in the effect of epsilon 0 and the constant for pi. Okay, the sampling of your space is set to 0.1, and we define the sheet, the surface charge density, to be a square of size 100. Okay, so now we set up the space. All right, and then we initialize the electric field vectors. So since we have 2 dimensions, we have 2 for loops. So each for loop will add the effect of the different points that it passes through to your uh, to your electric field component EX, EY, and EZ. Okay, so it passes through each point on the sheet, okay, based on this sampling rate right here. Okay, so now we just set the electric field to be 0 at the surface charge. Okay, because if it's not set to 0, then you will get a none, or an infinite value for your electric field, and you won't see anything in the plot. Okay, and You multiply this SAMP squared because you're doing numerical integration. You add everything up. If you don't do this, you won't get the actual value of your electric field. You actually get a larger value compared to what you can find when you're doing analytical solution. Okay, right? So this is just a plot, and let's run it. Okay, so since you're doing a nested for loop and you're expecting what this is 0.1 and your sheet is from negative 100 to 100, you're processing a lot of data to solve for the surface charge density, and that's okay. So it will take a long time before it finishes. Okay, not a very long time, maybe 5 minutes tops. And depends on your computer actually, of if how strong your computer is. So anyway, let's wait for it to finish. Okay, so now you see the result here. Not clearly, so let's just rotate it so you can see. There we go. So according to theory, the surface charge density emits a constant electric field that's perpendicular to the charge density, and it will be directed away from the charge density, as you can see here. So the theory actually coincides with what the numerical result says. Okay, you can maximize that so you can see better. There you go. So the length of the lines, the field lines, are equal, indicating that it's constant anywhere in space. So the theory, the analytical solution, agrees with the numerical solution. So you can be confident with your analytical solution when you're able to do this, and you're able to observe it in numerical solution. Okay, and it makes you more confident with your answer, right? Okay, so now let's look at a case where you have a line charge density, and it's not on the z-axis. Rather, it's a line defined by, oops, sorry. It's a line defined by this equation right here. Okay, so it's skewed. It passes through the origin, but it's skewed. Okay, so it's just based on this code, but I changed some uh, values. Okay, so let's see if it works. There we go. Okay, so I can't see any arrowheads. I've been trying to look for the setting here, but I can't find it in Octave. It looks better in MATLAB actually, but I won't be able to show it to you here. Anyway, you can see that the field lines are actually perpendicular to your line charge density. Okay, even if it's skewed. All right. Okay, so this is the code for that. Uh, I'll be happy to share it with you if you request me the code. All right, and that's the end of this video. All right, let me know if you have any requests via the comment section below. And thank you for watching, and I'll see you next meeting. Okay, bye bye.